The first question we're going to look at is 27. 27 gave us r squared sine 2 theta equals 2. On this one, my bet is, without looking at the answer key, that they probably went and swapped this out for something, and you're like, where did that come from? And it's a trig identity, 2 sine theta, cosine theta.
Yeah.
Where did that go?
So that's a trig identity that you are, quote unquote, supposed to know. I've never seen it necessary on any AP test ever, but that is a trig identity that you looked at in Algebra 2 and in pre-calc. Then once we make that substitution, it's tempting to change that r squared into x squared plus y squared, but what I'm going to do instead is separate it. Since this is all multiplication, I'm going to put one r with the sine and one r with the cosine. Okay, it's not like distributing because I don't have any adding here. I'm just kind of separating those r's since it's all multiplication and saying r squared is r times r. So I'm putting one of the r's with each of them. Then r sine theta is y. R cosine theta is x. And so this thing ends up being y is equal to 1 over 2x.
Why is 2r cosine theta?
I gave the r squared. I gave one of the r's to each of those.
But why did you give a 2 to each of those?
Oh, I don't know. Good question. So then it's that instead.
See what's up?
30. 30 is the same type of problem. We want to take our polar and turn it into x's and y's. Did they throw trig identities out on this one again?
Because this one doesn't even have an r in it.
They just multiplied both sides by r squared and then
Okay.
put the square outside of it.
Okay. So we can do whatever we want to an equation as long as we do it both sides. So we're going to multiply an r squared onto both sides of this. And then since everything is squared on a side, we can take that squared outside. Our cosine theta is x, and our sine theta is y. And this is fine for the curve. If you were asked to identify, what it looks like, you probably have no clue what it looks like in this format. And it did say identify or describe the graph. So then what we need to do is turn this into the conic section that it really is, which is going to be a hyperbola.
Sorry, what's a conic section again?
Oh, wait. Nope, just kidding. Not a hyperbola, because it equals 0. So that would have a hyperbola with a length of 0, which doesn't work. So we'll just take a square root of both sides, and y is equal to plus or minus x. So it's both of the linear curves of that. And the other one, if we look at the graph of that, it's the graph of a hyperbola. Um, 36, same type of problem, and on this one I'm sure they threw out some trig identities because we have a sum inside of a sine. So we would need to apply our sine sum formula, which is sine of first, cosine of second, plus cosine of first, sine of second. The kind of things that waste space in my memory. Again, this is one of those things that you are, quote unquote, supposed to know, but I've never seen you need to know it on the AP test. So then I've got an r out front of this whole thing, so I can distribute that. R sine theta becomes y. Cosine of pi 6 is 30. Cosine is square root of 3 over 2. R cosine theta becomes x. Sine of 30 or pi 6 is 1/2. And so we could solve this thing for y, but it's going to be a linear equation.
What does that do?
You were asked to solve it for, or replace it in with x's and y's, and then to describe the graph. So this is just going to be that's the description of the graph, that this is going to be a linear equation. And if you would graph this in regular mode, or if you would graph the original in polar mode, they should look exactly the same. It should be that same line that they would graph. The next question was 48. 48 asks us to do the opposite process and start with an xy equation and make it into a polar equation. I'm going to begin by squaring both of these things out. So I get x squared minus 6x plus 9. And y squared plus 2y plus 1. Then I'm going to take the x squared plus y squared, and that becomes an r squared. The minus 6x is going to become a minus 6r cosine of theta. And the plus 2y is going to become a plus 2r sine of theta. And then I have plus 10 equals 4. And I mean, I don't know how much you really need to simplify this. I'm bored with it. I don't want to go through the process of simplifying it. It doesn't really simplify very nicely, so I think this is good. It just said to replace it with a polar equation, and this is definitely a polar equation, so I think we can be done with it. 51 wanted you to graph the given curve, and then it asked what is the shortest length of a theta that can still produce the whole graph. So we need to go into polar mode. So down on that fourth line down, I need to change this thing over to polar. And then when I go into my y equals, it's actually an r equals. The equation that we're given for number 51 is an r squared equation. So we actually need to do a square root. We have to get r alone, so we're going to do the square root of negative sine 2 theta, and we need the negative of it because when you take a square root, you need the plus or minus. So I need the negative version of that as well.
How'd you get y1?
If you go into vars and choose y vars and then function, it'll allow you to reuse any equations that you've already put in, or you could just type it all in again. But then for my zoom, I'm gonna go zoom standard on this. Oops, what's invalid?
Mine did the same thing. You just gotta redo it.
Just have to redo it.
It worked for me.
What is that?
Wait, why do you have 2 bars?
What? Oh. Try to get it out. Yeah. Oh, I clicked zoom fit at first. Maybe that'll help.
It doesn't like my equation. What's wrong with the equation? Oh, it's probably because I can't use y1 because this isn't a y, it's an r. So that's my problem, is I can't do y1 because it's not really a y. So I'll just type it in again. Negative sine of 2 theta. All right, and then now it'll work fine. So we get that little bow tie thing. Then if we go into window, we have some options of what we're seeing. We're seeing x's and y's just like normal, but then it also gives us this theta interval. The default is 0 to 2 pi, which for most polar graphs will graph the whole curve. Sometimes it'll actually trace over the curve like twice. And so the second part of this question says, what is the shortest length a theta interval can have and still produce the graph? So I guess the first thing I would want to check is am I even seeing the whole graph? So instead of this is 2 pi, what if I go and put in like 4 pi? Do I end up seeing more than just a bow tie? Do I end up seeing like a whole flower or something? Nope, I'm still just seeing the bow tie, and it's tracing it over. So then now I would say, well, did it really take the whole 2 pi to do it, or was just 1 pi good enough? So I'd go and change that to pi and try graphing it and see if I get the whole thing, and I do. So it must be that 2 pi traced it over. Well, pi's good. Is pi halves good enough? So then I'd go in and try, how about, can I do this in just a pi halves?
It's a lot of guessing checking.
And I don't see anything. So definitely can't do it in just a pi halves because that's nothing. So looks like 0 to pi is what we need to be able to see this. It is a lot of guess and checking. You can do it without guess and check by solving some pretty messy trig equations. So I just kind of prefer to guess and check it because I would rather do that than solve out the messy trig equations that come up here. One way that you can kind of guess by looking at your equation is the fact that this had a 2 theta. Since it's doubling that theta, that means we're probably going to be able to get the whole thing done in half the amount of time and kind of work backwards that way. It's not a hard and fast rule, but that can kind of help you along in the process. But since if it was just a theta here, then we would probably need the full 2 pi. But since it's doubled theta, we can probably get it done in half the time. All right, so that was our reminder of polar curves. Today we're going to look at how you do calculus on polar curves. So the first thing we're going to talk about is the slope of polar curves. To find the slope of polar curves, what I suggest doing, you don't have to do this because there's a huge, big, messy formula that you can do otherwise, but I'm not a formula person. What I would suggest doing is writing your curve as a parametric equation using our substitutions that we learned yesterday. So for example 1, our equation is r cosine of theta, and it asks us to find the horizontal and vertical tangents. So to find horizontal and vertical tangents, we need a slope that we would set equal to 0 and undefined. To find the slope of a parametric, what we're going to do is say that x is equal to r cosine of theta,
Y is equal to R sine of theta.
and y is equal to r sine of theta.
Can I say?
And then we're going to find our slope parametrically.
Wait, how did that work?
X is equal to r cosine theta, so I'm just going to take r and plug it in,
So it's just an extra step, and then you do the
Oh.
parametric.
and y is equal to r sine theta,
Yeah.
so I'm just going to plug that in. So then we're just going to do parametric derivatives. Now when I say we're just going to do it, we have a product rule to take care of here. So for our x derivative, we're going to have first d second, derivative of cosine is negative sine, plus second d first,
Sine of theta.
sine of theta, And then dy first, d second, derivative of sine is cosine, plus second, d first. So then the derivative is dy over dx. I'm going to do some distributing. So I'm going to distribute the cosine. I get cosine of theta minus cosine squared of theta plus sine squared of theta. On the bottom, I'm going to get sine of theta minus cosine theta sine theta.
Isn't it supposed to be negative?
Is what supposed to be negative?
Isn't sine supposed to be negative because it's the derivative of cosine?
Negative sine is the derivative of cosine.
Yeah, so the sine on the bottom should be negative. The sine of theta on the bottom.
I put a negative out front, and then I lost it. Thank you. I put it out there, but then I lost it. So it should be negative down there. Yep, and this should be positive. And then plus cosine theta, sine theta.
So dx is a negative there?
So yep, dx should have a negative out in front of that.
None of our examples are actually generally neat.
I was really hoping that in distributing something nice would happen, and it just really didn't. Because on the top, we got that sine squared plus cosine squared, kind of, but it's really minus cosine squared. So that doesn't turn out into anything nice for us too much. On the bottom, we do have a minus cosine squared, or cosine theta plus, what am I trying to say? These two things are the same. So we can make it plus 2 cosine theta sine theta. There's the minus sine theta out front. That doesn't really help that much. So this question asked for where we have horizontal and vertical tangents. So to find a horizontal tangent, we would want our slope to be equal to 0. So we would take this guy and set it equal to 0 and have to solve. That is more than I would anticipate you ever needing to do, particularly because this starts to require some trig identities.
It would just be 0, because then it's negative 1. It's 1 minus
That's
1
one
plus 0.
solution. One solution would be that theta is 0, but there are more solutions. 2 pi thirds and 4 pi thirds are also both solutions to this. But again, I think that's probably more than you would ever need to do. And then to find our undefined slopes or our vertical tangents, we would set that denominator equal to 0 and solve. This is maybe not as bad. I can factor out a sine. So that gives me negative 1 plus 2 cosine of theta. So then this is going to work where either sine of theta is equal to 0, which would be 0, pi, and 2 pi, or where negative 1 plus 2 cosine of theta is equal to 0, which would be where cosine of theta is 1/2. If cosine is adjacent over hypotenuse of 2 and next to the 1 is the 60 degrees or the pi thirds angle. But we have to find which quadrants this is talking about. So if you remember from Algebra 2 or pre-calc, our little trig quadrant rule.
Why can't we take,
All students take calculus.
from the blue work, why can't we take cosine squared plus sine squared and make it 1?
Because it's not a positive cosine squared, it's a negative cosine squared. So sine squared plus cosine squared is equal to 1. But that's sine squared
Oh,
minus
got it.
cosine squared. So yeah, we got our ASTC rule, our all students take calculus rule. It talks to us about quadrants. So if we're working with a pi thirds or 60 degree angle here, and I want cosine to be positive, I'm looking at those two quadrants. So then we get solutions of pi thirds and 5 pi thirds. So at those places, we would have a vertical tangent. To find the places we have a horizontal tangent, again, it's yuckier, so we won't solve that other one. So first skill for polars is finding a slope. To find a slope, turn it into a parametric with x equals r cosine theta and y equals r sine theta, and then just do parametric derivatives. Second thing with polars is finding area between two polar curves. This is usually part of a free response question. It's not always, but it always shows up somewhere, whether it's on a multiple choice or free response. Area is the integral from alpha to beta, just our two angles. 1/2 r squared d theta. We could go through why it has to be 1/2 the curve squared instead of when we're working with x and y equations. The area is just integrating the curve and why we have to do the 1/2 and the squared here. It comes from all of those substitutions and stuff. This is one formula that I actually just memorize. And you guys know how much I hate just memorizing, and I actually just memorized this because trying to derive this formula is not something that I want to spend my time doing.
This is for the area of a polar graph.
This is for the area inside of a polar curve. So, example 3 wants us to find the area enclosed in this curve. And this is where that last homework question that we went over can become kind of important, is in finding out what limits of integration we need. So when we graph this function, it looks like this. It's a cardioid. And our limits of integration would be the minimum that it takes to draw out the whole curve. So we were doing some kind of guess and check, and I said most of the time it's going to be 0 to 2 pi. But that's not always true. So this is where we'd want to kind of do some guess and check on that and see, could it draw out the whole thing with just a 0 to pi? And if so, those would be the limits I would need. But on this one, it does take the full 0 to 2 pi to draw it out.
Whenever we have something like that, will it always be in a calculator portion?
Not always. Most ways.
Okay, so if it was
So.
if it wasn't on a calculator portion, we assume it's not it is
Yeah,
just a 2 pi.
yeah, I would just go 0 to 2 pi.
Do you wanna err on the larger side?
You don't want to err. If you do extra, like if it could be done in 0 to pi,
Yeah.
and you do 0 to 2 pi, it's going to give you double the answer.
Oh.
And on a multiple choice, it'll be there.
Oh.
You
So
know,
we're just supposed to know
'cause
by
they do that.
graphing this?
By graphing, yep. And using that window and kind of guessing checking it.
Alright.
So then we go 1/2 of r, which is our curve, to 1 plus cosine theta squared d theta. I don't know that I've ever seen one of these on a non-calculator in terms of actually needing to do the computation. So I think this is a fininter.
How do you finish something that's
The book actually goes through the process of trying to do it, but in doing that process, they're using trig substitutions, which we don't really need to do. So this is going to be a fininter. You want to be careful in plugging it into finint. There are a lot of parentheses there. There's a lot of parentheses. So I'm going to go Math 9 is finint. I actually don't type in the 1/2 because that's not being squared. So then I'm just going to worry about the half at the end. I'm just going to multiply my answer by 1/2. So I just want to do my curve squared. My curve is 2, 1 plus cosine of theta. Let's see, I opened 1, 2, 3. Close one more. Squared. And then comma, variable, comma, 0, comma, 2 pi. I'm still in polar mode, but you don't, oops, not 2 theta, 2 pi. You don't have to be. It'll work fine if you're in regular x and y mode and you'll just be using x's instead.
You put the squared outside the third parentheses, which I think it needs to go in the second, because then it's included within it.
No, the 2 squared.
No, I opened 4 parentheses before
Everything
that,
was
so I
included
only
within
closed
there.
3.
Oh, okay, sorry.
This is why I wish they did parentheses in color. Like you open a red one, you close a red one. You open a blue one, you close a blue one. That would be great.
Oh,
They should give us 3 colors.
Yeah, GeoGebra does that, and there's other like computer programs. When I took
Oh, yeah.
calculus in college, there was a program that we had a calculus lab. And we had to do stuff in there, and it did that too, and it's so nice. But so that's the area. And close. Oh, but not yet because it's 1/2. So then I always forget to multiply by half. Don't forget to multiply by half.
Nope.
So multiply by half.
If I don't have right prep, screwed.
So
So you better.
Notepad++ would have colored parentheses.
the next example
Random fact.
is another area example. It wants us to find the area inside of the smaller loop of a curve. So actually, let's just look at the graph of this curve. So the curve that it gives us is 2 cosine of theta
This one?
plus 1. And I'm going to graph that. Oh, but my window is set to have a really small theta right now, so I'm going to go and change that back to a 2 pi. Okay, so then I see my whole curve. This is that French word that I can't say. It kind of looks like lemon, except it has like a C in it. I don't know, limison. I don't know how to say it.
Mine, like, I'm plugging everything in, but I can't get it to, like, draw the picture. And I did it, like, right away for the last picture, but it, like, won't do the picture. I'm in color form.
I always get T step. We want that to be like a really small number.
Okay. Thank you.
Our upper limit's always multiples of pi.
Yeah. I mean, well, it could be like a pi halves or a pi
Yeah.
thirds or something like that, but it's always, yeah. So this question wants us to find the area just inside of the little circle, not inside of the whole thing. So what we're going to do is trace on our curve and find out where that little circle is. So it starts at a theta value of 0. Notice it gives you a theta and an x and a y. It starts at a theta of 0. And I'm going to trace around this thing until I get to x is 0 and y is 0, which is essentially here. And that gives me my theta value. So that's going to be our lower limit. Is going to be that theta value. So I'll write that down. 2.094, which is probably some nice something of theta, like 2 pi thirds. But, you know, we're not going to worry about that. And then I'm going to keep on tracing until I get back to 0, 0 again, which is about here.
It is 2 pi.
And I get, I know I cheated and looked in the book. 4, because they do it by hand. 1, 8, 9. And those are going to be our limits of integration on it. So again, you can find those values by setting our equation that we're given equal to 0, because that would give us a radius of 0, and then that would allow us to solve it. So I mean, it actually doesn't turn out to be that gross in terms of solving this particular trig equation. Because since that inner loop begins and ends at the origin, where the radius would be 0, I can set r equal to 0 and solve this equation, which if we're working with adjacent over hypotenuse, that would point us to our 60 degree. And if I want it to be a negative 1/2, I would want it in those two quadrants. So that gives me the 2 pi thirds and 4 pi thirds. So we're going to integrate from 2 pi thirds, or the messy decimal the calculator gave us, to 4 pi thirds. 1/2 our curve squared. But this is going to turn into a finite problem. Again, the book doesn't even solve this one out by hand, which is why I'm fine just using the decimals instead of finding the 2 pi thirds and 4 pi thirds, because if we can't integrate it by hand, then why should we bother finding the other part by hand? Just go ahead and do the whole thing on the calculator and throw that in finite, and I get 0.544.
What are you in radians or degrees?
It doesn't actually matter. Oh, radians or degrees does matter. You have to be in radians. Oh, that could be why you weren't getting a graph.
Yeah.
Is it safe to assume that if we're using pies, we're always in radians?
What?
Is it safe to assume that if we're using
Yes, if pi's are in there, we're always in radians. In general, always radians. The only exception to that is if the problem specifically gives you an angle measured in degrees. If the problem specifically says, and we really only do that in this projectile motion problem, so something's launched at a 45-degree angles, switch it over to degrees. Otherwise, radians all the time.
If you were really like snobby, could you like change the radians into degrees?
Yeah.
If I have, like,
Change the
extra time,
radians into degrees, not if you're going to take any derivatives. Change degrees into radians. Because the derivative of sine as cosine is only true in radians. So if you start to work in degrees, then you're going to get wrong answers.
Why radians are what they are?
It's one of the reasons why radians are so important to us, because otherwise students are like, why bother? Let's just do degrees for everything because that's more visual and I can see that better. So that's one of the reasons why they're so important, is because calculus doesn't really work very well in degrees. We'll go ahead and stop here. We're not done with this section. I've left 2 examples, so we'll do these 2 examples on Monday when we return. Start reviewing. We'll review the rest of the day Tuesday, and we'll have our test on Chapter 10 on Wednesday when we return.